Hi, welcome to Nuclear Chemistry Podcast 1.3C, broadcasting live from Harper Creek High School. Let's just review some of the things that we've learned this week. One is this graph of neutrons over protons. As you can see, helium has two isotopes, one with 2 neutrons and 2 protons, 2 to 2. And the other isotope is 3 as a mass number, which would be a total of 1 neutron and 2 protons. So that's your Y value. And then on the x-axis would be 2 protons. So the definition of an isotope, reviewing that again, is that you have 2 atoms of the same number of protons but different neutrons. So they're the same elements, different mass. Here is a more expansive chart of the same thing, but you can also see that there are, in the dark region, the most abundant isotope. The red would be other isotopes, and radioactive would be the clear ones, the ones that are unstable.
Mr. Beach, will I call the office?
There's a band of stability, that's what they call this, and the first 20 would be where you have a 1-to-1 neutron to proton ratio, and that kind of becomes a steeper slope where you have to have more neutrons for stability and for isotope existence at all. So that's interesting. And this gives you just a little closer view of close-up view of what the larger graph represents. You have alpha decay, where we've talked about this week how if you have alpha decay, you have a particle that loses 2 protons, so you go back on the periodic table 2 spaces. Here, uranium, after it gives up a helium atom or an alpha particle, becomes thorium. The beta decay, however, causes one to jump forward on the periodic table 1 space. So carbon, if it gives up a beta particle, it actually becomes new nitrogen, as it actually gains a proton from the decaying nucleus. Radioactive decay of carbon-14, this just shows you that this unstable particle breaks down over time and is really good for measuring how long something has been around within the first 10,000 years. This here shows how alpha particles can be stopped by paper, beta particles can be stopped by lead shields, and gamma rays, a little more penetrating, can only be stopped by concrete. The difference of fission versus fusion, just remember that in fission, that definition is for the nucleus to split. So typically what happens is a neutron hits this particle and it breaks down into smaller ones, whereas in fusion, the original particles are combining to form larger nuclei. Nuclear chain reactions occur in fission. They're actually quite dangerous, where they can get out of hand. So this uranium-235 particle splits into 2 particles. The dangerous part are these neutrons that are also emitted. They now provide the bowling ball, or the momentum, for more uranium to be split. So here are a couple problems for you to do, and I will do them along with you. Remember, we're trying to balance the equations just like we have in chemical reactions. The only difference is that we're forming new elements. You can't do that in chemical reactions. So aluminum here has a mass of 27. This beta particle, so this is a beta decay reaction, has 0 mass. So this mass, to balance it out, must be 27. On the bottom here, aluminum has a proton number of 13. So the bottom values here, -1 plus 14, add up to 13. And so you look up atomic number 14 on the periodic table in silica. This one, it's the same thing. We have a nuclear reaction here where the left side must add up to the right side, mass as well as the bottom proton values. So the top here, 27 plus 4 is 31. Therefore, 30 plus 1. So you have to have a 1 up here. And the same thing on the bottom, 13 plus 2 equals 15. So therefore, 14 plus 1. So again, you have to put a 1 on the bottom. So if you look up atomic number 1 on the table, it's the first element, which is hydrogen. Problem number 3, you're just coming up with 2 hypothetical elements that might fuse to make gold. So you have this one here could possibly be, you might have copper. Find my pen here. Oops. So you might have copper here. Somehow got out of the pen mode. You might have copper here. And you might have another element here, such as